Welcome back. Today we're studying Unit 4, Polynomials and Quadratics. Specifically, first unit, which is 4.1, multiplying and factoring polynomial equations. So if you open up your packet to that page, hit pause if you don't, we have a blue rectangle and an orange rectangle with the dimensions 2z by z. But the orange rectangle looks like it has about the same height, so let's call that 2z. And let's give it a width of 8. So the area of the blue rectangle would be z times 2z, height times width, or 2z squared. The area of the orange rectangle is 2z times 8, or 16z. Now, imagine putting these two rectangles together to make a larger rectangle. The height would still be 2z, but the width is now z and 8, or z plus 8, which means the area would become 2 times z plus 8. Or z squared plus 16z. Notice that's the same as if we were to add the two individual areas separately, which means that we can either calculate the areas separately or all together. Let's take advantage of this to study another particular case and see how many different ways we can represent an area of a field, which is 3a squared plus 3a. We need to find the length and width of the rectangle. So let's draw ourselves a couple different scenarios to see if we can come up with some solutions to the length and width of a rectangle that has an area of 3a squared plus a. So in the first case, we'll study to consider what could possibly be the height of this rectangle. Well, we notice both of them have 3 in common. So it could be 3 was the height, so that would make this part a squared and a. Or maybe a was the height, in which case we can kind of multiply it out an a from each. Or if we actually take 3a out, we can divide each by 3a, so the width would be a plus 1. Each of these rectangles represents a different way to write the possible multiplications that could equal 3a squared plus 3a. So I could say 3a squared plus 3a could be 3 times a squared plus a, or it could also be equal to a times 3a plus 3, or it could be equal to 3a times a plus 1. This one is the fully factored form because there are no other factors in common between the two pieces of the original. Let's use this idea to write some of the problems below as multiplication problems. If I look at number 1, 10ab plus 5a, well, what do both terms have in common? They both have an a. Both 10 and 5 are divisible by 5. So if I take out that 5 and that a, I can say that it's the same as 5a times, well, 10 divided by 5 is 2. A divided by a is 1, so that leaves 2b, plus 5a divided by 5a is 1. It's key to notice that that second term doesn't vanish, but rather once something divided by itself, it becomes 1. Similarly for number 2, notice how 3 and h are in common between all the different terms. You may want to pause and just see for yourself if you agree if that's the greatest common factor, the largest number that goes into your both. As I divide out each term by that greatest common factor, I'm left with 3h times the quantity g squared minus 3g squared plus 4h. Looking at this last one, you'll see that I've given you the factorization. Use that as an opportunity to test yourself and see if you understand the factorization. Factoring is the reverse process of multiplication. We factor a polynomial by reversing the distribution problem, factoring out the GCF of each term and writing on the outside of the parentheses. To check whether the polynomial's factored form is equivalent to the expanded or multiplied form, you can multiply the factors to see if the product yields the original polynomial. Like, for example, 4 times quantity x plus 3, if I distribute it, is 4x plus 12. So we would say that it is the factored form of 4x plus 12. We know that a non-zero polynomial expression with integer coefficients is said to be prime or irreducible over integers if it satisfies the two conditions. Number 1, it's not 1 or negative 1. And if it's written in the product of two polynomial factors, each with integer coefficients, that means whole numbers, then one of the two factors must be 1 or negative 1. We can factor more of these using a table as a support. You have seen a geometric area model used in previous examples to demonstrate the multiplication of polynomial expressions, when each was known to be a measurement of length. In other words, something we could draw as a rectangle. But without length, we cannot be certain that a polynomial expression is positive. Therefore, an area model isn't really exactly applicable to all polynomial multiplication. But a table can kind of be used in a similar fashion to see the different parts of the product or multiplication as we multiply them. The table serves to remind us of the area model even though it doesn't represent area itself. So in the example of x plus 2 times quantity x plus 5, we can imagine a rectangle where x plus 5 and x plus 2 are on each side. Each one is a little area like an x by x is x squared, 5 by x is 5x, 2 by x is 2x, and the last part is 10. We can add up each of the individual areas to say what the product of x plus 2 times x plus 5 is. So we would have x squared, we'd have 5x plus 2x, and then 10. The 5x and the 2x combine for a final answer of x squared plus 7x plus 10. We can then use this in turn to explore difference of squares. Find the product of x plus 2 times x minus 2. Use the distributive property to distribute the first binomial over the second. This is Mrs. GH style, or foiling. X minus 2 times x plus 2. We have to distribute x minus 2 to both the x, as in x times x minus 2, and to the 2, plus 2 times x minus 2. We then repeat the distribution, going x times x is x squared minus 2x plus 2 times x minus 4. We notice the middle terms cancel, leaving us with x squared minus 4. If we examine this in the table method, notice the similarities. We have x plus 2 by x minus 2. X times x is x squared. 2 times x is 2x minus 2x. And then minus 4. We can add up each of these partial products, as they're called, or each of the pieces of the table. So we have x squared plus 2x minus 2x minus 4. Notice it's the exact same expression we got by foiling. The middle terms in turn cancel, and we get the same result. Which method you prefer, as always, is a preference of style. Let's use what we just did to see if we can come up with the examples of how we would find perfect squares, like t minus 25. Well, if I know that I'm multiplying two binomials, then I know something times something is t squared, and I know that the middle terms have to be opposite, so I need a plus and a minus. I know they multiply to be 25, so plus and minus 5, and then t and times t gives me squared. Similarly, for the next one, notice how the first plus and minus, then the square root of 9 is 3. The square root of 4x squared is 2x. So 4x minus 9 is 2x plus 3 times 2x minus 3. Notice how each term is the square root of the two terms of the difference of perfect squares. So for C, we can look at the perfect squares. We can already say that it's going to be the square root of 16h, or 4h, plus the square root of 36, or 6. So 4h plus 6k times 4h minus 6. For part D, there's an interesting dilemma. Notice how the 4 is first and the b is second. It still applies. 2 minus b, 2 plus b. The variable doesn't have to be first. Likewise in E, the root of x to the fourth is x squared. That's x squared minus 2 and x squared plus 2. Apologies, it looks like I wrote plus 4 there. And then for the last one, x to the 6 has the square root of x to the third, because x to the third times x to the third is x to the 6, minus 5 minus 20, x to the third plus 5. So we can say as a general rule that if we have a squared minus b squared, that's equal to x plus a plus b times a minus b. This relationship, a plus b and a minus b, are called conjugates. Put that in the back of your mind. It's going to show up again. And apologies, this plus between the a squared and the b squared should be a minus. Special case we're going to look at now is what's called the square of a binomial, or when we have two things being added, like x plus 3, multiplied by themselves. So the first thing I suggest is actually write out x plus 3 times x plus 3. We do the distribution, we get x squared plus 3x plus 3x plus 9. Notice that the first and last term are x squared, a perfect square, 9, a perfect square, and the middle term is twice the roots. That's the key pattern that we're going to use throughout. So a plus b squared, let's write that out, a plus b times a plus b. We're going to distribute a, so that's going to be a squared, plus ab plus ba, inside, outside, inside, using foiling right here, plus b squared. Again, use whichever method of multiplication makes the most sense to you. Notice ab and ba are the same, so we can add them as 2ab plus b squared. Notice, again, the same, the only difference is the negative in the middle. So a minus b squared is a minus b times a minus b. I really suggest multiplying it out. This pattern, we can expect that there's going to be a perfect square in the middle, a perfect square at the end, and double the root. So we have a squared, again, that perfect square in the middle, minus ab, minus ba, outside, inside, and then last gives us plus b squared. Combining like terms, we get a squared minus 2b, because multiplication doesn't matter, ab and ba are the same, plus b squared, and we get perfect squares and double the roots. Perfect square at each end, and in the middle, double the roots. Perfect square at each end, and in the middle, double the roots. Anything important, say 3 times. So to summarize, we've looked at how to use the area model to factor, how to represent that as a table, how to find greatest common factors, 2 special cases, the difference of squares and perfect squares. And now I'm going to wish you a